Okay, today we are looking at Big Bang and the atom and how everything ties together. We've looked at electrons, valence electrons, ions. We have looked at how things work on the periodic table, and now we are looking at all of those things in reference to each other and why they act the way they do. The first main question is, what is the pattern or trend within the periodic table of the atomic structure? Well, atomic structure comes in multiple ways. We're first going to look at core and valence electrons. Then we are going to look at atomic radius and ionic radius. So when we are looking at core and valence electrons are the electrons in those outermost rings, and they go up across groups, across periods, and they remain the same down groups and families. Basically, they increase left to right. Now, if you are looking at your periodic table, the left-hand side is always your alkali metals, and the right-hand side is always your noble gases. It's really important to have that reference point in case you are me, like a teacher, where I always do things backwards and then confuse everybody. The core electrons are fairly stable on a period, but they increase per group, and these are the electrons that are not valence electrons. So these are the electrons that kind of get captured primarily in the noble gas formatting that we use to make sure that that's how it works. And it's fairly stable from on a period. It increases top down. Now look, after the D block, the P block is slightly higher than the S block because you're adding in those 10 extra valence electrons suddenly from that D block jump. Okay, if we were looking at valence electrons and core electrons in terms of diagramming them on a periodic table, you would draw the arrow for valence electrons from left to right because that is the way they increase. You would draw the arrow for core electrons from top to bottom because that is the way it increases. The biggest hint that I can give any student is to always draw your arrows towards increasing. Drawing an arrow and then writing the word decreasing on it is counterintuitive and will make you confused when drawing your patterns and diagrams. I've seen very many students draw proper arrows and then improperly label them increasing and decreasing. Whereas if you always do your arrows towards increasing, you will not have to then remember what words to write on which arrows. Okay, if you flip your periodic table over and make it a side-by-side, we can work through the definitions, trends, and the why. And that why piece is what ties everything together. So, valence electrons. These are the electrons in the outermost quantum number. This is those shell rings. If you're drawing your Bohr models, these are the electrons in that outermost ring that we identify as valence electrons. If you're doing your quantum map, they're the ones on that highest quantum orbital shell. So remember the trend, it increases across periods, left to right. It's pretty much no change, same down the group. That is because each family is the same. Now the why is remembering how to understand how columns relate to quantum numbers and orbitals when writing your electron configurations. Every element in a column and family has the same final orbital. Yes, you might be at a different quantum number, but it is the same final orbital. So all of everybody in column 1 ends with S1. Everybody in column 2 ends with S2. So S1, 1 valence electron. S2, because it's a full shell, 2 valence electrons. Everybody in column 13 ends with P1. Well, if you add 2 plus 1 from S2, and then 1 from P1, you end up with 3 valence electrons. When you look at column 14, it ends up with P2, and then 2 plus 2 from the S2, 2 from the P2 gives you 4 valence electrons. So basically you're adding a valence electron per column you move. Therefore, it increases at a steady rate. But because every column has the exact same ending orbital, it doesn't change the valence electrons. Okay, let's talk about our core electrons. These are the electrons in an atom that are not, I repeat, not the valence electrons. The trend is that it increases down families, but is fairly stable across periods. For periods 1, 2, and 3, the core electrons will be the same for all the way across. When you hit period 4, because now you're adding in those valence electrons and electrons from the D block, you get a slight increase, but it's still fairly stable. And you get that increase from the S to the P block. The formula is for core electrons is total electrons. Reminder that total electrons are your atomic number, or your atomic number plus or minus the electrons you're adding or subtracting for an ion, and your valence minus your valence electrons. The Y is that core electrons are stable as they are already filled levels related to the previous noble gas. These core electrons are what you are referencing when you do things like HE in blocks and then say Li. So He2S1 works because you're basically saying referencing core electrons plus then your valence electrons, or electrons at the quantum level. So we've used core electrons, we've used valence electrons, and now we're trying to explain how they all work together. So this shouldn't be a brand new concept if you've been using noble gas configuration. Okay, now it's time to do some practice with total electrons, number of valence electrons, and core electrons with the challenge ones of 2 ions down here in the term of the chlorine ion and the iron ion, to see if you remember how to use those electrons as well. I'll give you a few minutes to try them and write down the answers before we go over them. If you're watching the video, pause now to do the practices. Okay, let's walk over the answers, or through the answers for the practice valence and core electrons. So the first setup we were given was just magnesium, that's Mg. So if you look on the periodic table, the number of valence electrons for magnesium is 12. And then you have 2 valence electrons. This is in column 2. So 12 minus 2 gives me 10 core electrons. If we're looking at nitrogen, and nitrogen does not have an ion, it's got a plus or minus, so we just look at nitrogen. It has 7 electrons because the atomic number of nitrogen is 7. It's in column 15, so it has 5 valence electrons. So 7 minus 5 gives me 2 core electrons. Finally, not finally, but we're looking at Cl1 minus. That's chlorine, but it's a chlorine ion. So if you look at chlorine, it has 17 valence electrons, but we've added an electron for a total of 18 valence electrons. Sorry, 18 total electrons. That one we've added, gone to the valence electrons, we have 8 valence electrons. So 18 minus 8 gives me 10 core electrons. And finally, iron. If you look at iron, it has 26 electrons, but we have a 2 plus charge, which means we're losing 2 electrons. So 26 minus 2 gives me 24 total electrons. Those 2 generally get lost from the valence shell, so we have no valence electrons. So we end up with 24 core electrons. Moving forward, what are the periodic table trends for the atomic radius, ionization energy, and electronegativity? We are going to look at this in 2 sections. We're going to look at the atomic radius and the ionic radius because they go very well together. We're also going to look at it in terms of ionization energy and electronegativity because they go very well together. Moving forward, atomic radius is the size of an atom. Electronegativity is the atom's attraction to other charges, and ionization energy is the amount of energy needed to remove an electron. Please listen to me. I understand that there's this arrow that has the words decreases on it. I'm going to show you the arrows that are increasing, so you do not have to remember to write the word decreases and get things wrong. So we are going to look at the trends for atomic and ionic radius. Atomic radius is in pink, ionic radius is in blue. The atomic radius increases from starting at noble gases, which are the smallest atomic radiuses, all the way over to alkali metals, which are the largest, and it increases down columns or down families. Ionic radius also increases down families. This trend matches, but it increases from alkali metals to increasing size over to noble gases. Okay, moving on to some definitions. The atomic radius is half the distance between adjacent nuclei and a crystal of the element, or it's a very, very fancy way of the atomic radius of an atom is the actual radius of an atom. If you kind of conceptualize that we have been working with Bohr models, and radiuses go like half the distance of a circle, you can put it together, and I made this lovely drawing right here. That's my definition of a radius in a Bohr model. The trends, verbalizing it, it increases across periods, right to left. It increases right to left. So noble gases to alkali, if you're looking at the periodic table, it increases down columns, and that Y is the important piece. The higher quantum numbers and more electrons are going down the columns. If you're looking and thinking of Bohr models, as you go down, you add more rings. Those additional rings take up more space and make for a bigger radius. If it really boggles some students' mind that there are more electrons over by the noble gases, so why would it have a smaller atomic radius? And if you think of protons and neutrons as kind of like magnets, there's more positive and negative over by where the noble gases are, so it squishes down and compresses more because there's more positive to hold the more negative down. Whereas over in the alkali metals, there isn't as many positive and negatives, so that they kind of have a more decreased area to hold them together. On the other side, if you have, looking at the ionic radius, now remember, and that's the atomic radius of an ion, that trend is important because it helps you visualize what's really happening when we talk about ions. So please remember, an ion is an atom or bonded group of atoms that have either a positive or negative charge. A cation are your positive ions. They often go from group 13 or the boron family on over to your left. So columns 1 through 13. Basically, your metals become ions or cations and become positive. If you have a really hard time remembering that, remember the old musical Cat on a Hot Tin Roof. You have cat on a tin roof. Cat is positive and tin is metal. Two go together in that musical. Okay, sorry. And now we're looking at ions. Anions are the negative ions that have gained electrons. This is often columns 15, 16, and 17. These are your non-metals. Metalloids are kind of somewhere in between and often act more like transition metals or don't want to give or take or make ions at all and share. So we don't really talk about them in the clear definitions of ions. The trend for the ionic radius, it increases across periods left to right, and it increases down columns. Now, the reason that this also increases down columns is no matter what's happening with the valence electrons, you're still going to have more electrons the more down you go. Think of it like, making a hoop skirt. It doesn't matter who the hoop skirt goes on, it's still going to be bigger at the bottom. Periodic table. But the reason that this trend is opposite of the atomic radius is that your anions over by the noble gases are gaining electrons. When you gain electrons, you get bigger. On the other side, your cations over by your alkali metals are legitimately losing electrons, so they get smaller. That exchange of electrons is what shifts your trend. Okay, now it's time to look at the trends for ionization energy and electronegativity. Yes, these are both the exact same trend. And both of these are important to note, have to do with francium and fluorine as a significant marker in the trend. So, if you box francium, that is the lowest amount of both electronegativity and ionization energy. And if you box fluorine, that's where your highest electronegativity and ionization energy is. If you remember, if you just draw your marker from francium to fluorine as an up arrow, that kind of shows you that trend. If you can remember, it goes from F to F, and then it increases across this way, and this one actually increases up columns. Let's talk through these definitions, trends, and the whys. So let's work through electronegativity first. Electronegativity is the relative ability of an element to attract electrons into a bond. Again, the trends for both of these are the same. They increase across periods left to right. So your alkali metals are the least, and your halogens are your most. And then they actually increase up columns, with the elements at the bottom of the columns having the least amount, and the top elements at the top of your columns have the most amounts. But the Y's are the most important. Everything on the periodic table wants to mimic noble gases. So if you think of things in terms of ions, because both of these really have to do with ions and creating bonds, anions already have 5 to 7 valence electrons depending on the column. So they are really close to those 8 valence electrons. So remember, 8 valence electrons is that full shell that elements are looking to get. So they can attract more because they're already close to 8. So they're very attractive because they're close to 8. Cations actually reach noble gas configuration by losing electrons. So if we're going to compare two of these, magnesium being in column 2, an alkaline earth metal, and having S2 as a orbital shell, so it has 2 valence electrons, loses 2 electrons to become a 2+ cation. By doing that, it actually mimics neon. Fluorine, on the other hand, is in column row 2, period 2. It's in column 17, though, so it has 7 valence electrons. It only needs 1 more to hit 8, so it has a 1- ion, or anion. So it mimics neon by gaining an electron, whereas magnesium mimics neon by losing 2 electrons. If we were looking at sodium, it would mimic neon by losing 1 electron, and oxygen mimics neon by gaining 2 electrons. So basically, everyone's trying to be noble. So if you're looking at your noble gas configurations, you're looking at how everybody gets to be noble. So if your noble gas configuration is really close to the next noble gas, it's probably an anion. It's really not close to the next noble gas. It's not in the P block. It's probably a cation. If you're looking at the noble gas, it is like at P1 or P2. P2 doesn't really form ions, and P1 pretty much forms cations. Ionization energy. This is the energy required to remove an electron from a gaseous atom. First ionization energy is the energy required to remove the first electron. If you think of energy as the currency of the periodic table, it's really how expensive an element is and how expensive they hold their ions. So if you look at the trends, it increases left to right across periods. So the alkali metals have less expensive ions or electrons than the halogen family, and the one elements on the bottom have very inexpensive electrons. And the why is really simple. The ones that hold on to their electrons are the ones closer to noble gases already, so they're going to charge you a lot of energy to take their electrons, because they really want to spend the money over here with electronegativity to get more electrons to come to them. They're the more likely reason to buy more electrons in energy. Whereas cations, they mimic noble gases by giving away their electrons. They want to get rid of their electrons. Hey everybody, take my electrons! So they're not going to charge a heck of a lot for the electrons that they want to get rid of in terms of energy. Please remember that everyone's goal is to be noble. If you are a cation, you become noble by shedding your electrons. If you're an anion, you become noble by stealing everybody else's. Okay, now that we talked about ionization energy and electronegativity, we can really look at some of these natural trends. So if you're looking at like the trends within a family, and we're looking at the alkali metals here, that's column 2, beryllium's going to have more ionization energy than barium because it's higher up in the column. Those that are higher in the columns have more ionization energy as you move down the columns. It decreases. So what are some explanations for the atomic radius, ionization energy, and electronegativity trends? We've looked at some of these, but here is some really nice examples. So remember the atomic radius, it goes down a group, means the greater number of orbitals, therefore it's going to be larger. When you're looking at the cross, it has the more positive nucleus, which pulls it in more. We've talked about this, we wrote it down, but here's a different way of looking at it. For ionization energy, when you go down a group, it has greater number of orbitals, therefore farther away from the nucleus. It's easier to remove when you're farther away. Same idea as being farther away and not being watched by your parents. The same number of orbitals, but left to right across periods, so it has a more positive nucleus. So again, it pulls it in tighter. Electronegativity is almost the exact same as ionization energy because it's the exact same trend. So how can the known and discovered trends be used to predict properties of a different set of elements? And how can this be confirmed? So when you're looking at a periodic table or you're looking at trends, you can compare the relative location of the elements in question and apply the known trends. You can explain what things are most likely to be based on trends. You might do this in a form of a performance task or such not as that.